welcome to this problem walkthrough. In this session, we'll explore the problem titled Number of Wonderful Substrings. We'll break it down step by step, understand the key concepts, and discuss various approaches to solve it efficiently. Let's dive right in. In this problem, you're given a string called word, which consists of lowercase English letters. Your task is to find the number of wonderful substrings in this string. Now, a wonderful substring is defined as any substring where at most one letter appears an odd number of times. This means that for a substring to be wonderful, all but at most one of the letters in it must have even counts. The output will be an integer, representing how many such wonderful substrings exist in the given string. For example, if the input string is ABA, the output will be 4, as there are 4 wonderful substrings in that case. The input constraints specify that the string length can go up to 100,000 characters, and it will only contain letters from A to J. This means the solution needs to be efficient to handle large strings. Let's break down the first example to understand wonderful substrings better. The input string is ABA, and the output is 4. The wonderful substrings here are where the letter A appears once, which is odd, and all other letters appear 0 times, which is even, B, where B appears once, which is odd, and all others are even, another A, which satisfies the same condition as the first one, and finally, ABA, where A appears twice, which is even, and B appears once, which is odd. All other letters have even counts of 0. These substrings satisfy the condition for being wonderful. For another example, if the input string is AB, the output is 9. Here, we count all single-letter substrings like A and B as wonderful, as well as two-letter substrings like AA, UB, and BB. Each of these substrings meets the condition that at most one letter has an odd frequency. In the AB example, we also have a 3-letter substring AB and a 4-letter substring AB that qualify as wonderful. Specifically, AB works because A appears once, which is odd, and B appears twice, which is even. Similarly, AB is wonderful because A and B both appear twice, making all letter counts even. Another example is the input string he, which results in an output of 2. Here, the wonderful substrings are H and E because in each case, the corresponding letter appears once, which is odd, while all other letters have even counts of 0. These examples demonstrate how the definition of wonderful substrings applies to different input strings. To summarize, a substring is simply a contiguous segment of a string. For a substring to be considered wonderful, at most one of the letters in it can have an odd frequency, while all others must have even frequencies. Examples like AA and ABA qualify as wonderful, while something like ABC does not because it has more than one letter with an odd count. Given the constraints, where the string can be very long, up to 100,000 characters, we need an efficient solution. Techniques like bit masking and prefix sums are well suited for this problem, as they allow us to handle the frequency conditions and the large input size effectively. To solve the problem of finding wonderful substrings, one approach we can consider is the brute force method. The intuition here is straightforward. For every possible substring of the input string, we check if it meets the condition of being wonderful. The steps are as follows. First, we generate all substrings of the word. Then, for each substring, we count the frequency of each letter and check if at most one letter has an odd frequency. If the condition is satisfied, we increment the count of wonderful substrings. While this approach is simple and easy to understand, it comes with significant computational drawbacks. Generating all substrings has a time complexity of O(n) squared, and for each substring, counting the frequencies adds another O(n) per substring. This results in a total complexity of O(n) cubed, which becomes impractical for larger strings, especially when the input size can go up to 10 to the power of 5. Therefore, this approach is not feasible for this problem due to its inefficiency. To address the inefficiency of the brute force approach, we can use an optimized method based on bit masking. The key intuition behind this approach is that instead of explicitly examining each substring, we can efficiently track the parity, or odd/even status, of the frequency of each letter using a bit mask. A bit mask is a 10-bit integer where each bit represents the odd or even frequency of one of the 10 lowercase English letters from A to J. For instance, a bit mask like 001, 011, 0000 in binary indicates that the letters C, D, and E have odd frequencies, while the rest have even frequencies. The critical observation here is that a substring is considered wonderful if at most one bit in the bit mask is set, meaning at most one letter has an odd frequency. Using this idea, we can adopt a prefix-based approach to calculate the bit mask for substrings ending at each index of the string. To efficiently count wonderful substrings, we keep track of how many times each bit mask has occurred so far. For the current bit mask, it forms wonderful substrings with all previous occurrences of the same bit mask, as their XOR results in the same mask. Additionally, we consider substrings where exactly one bit differs, achieved by flipping each bit in the mask one by one, which represents one odd letter. To implement the optimized approach, we follow a series of steps. First, we initialize a dictionary called prefix_count to store the frequency of previously seen bit masks, starting with an initial bit mask of 0, which assumes all letters have even frequencies. Then, we traverse the string while maintaining a current_mask that updates based on the parity of the current character. For each current_mask, we add the count of substrings that share the same bit mask from prefix_count. We also add the count of substrings where exactly one bit differs, which is achieved by flipping each bit in the bit mask. After processing the current character, we update the prefix_count dictionary with the current bit mask to reflect its occurrence. Finally, after processing all characters in the string, we return the total count of wonderful substrings. This approach significantly improves efficiency, as we only traverse the string once, performing constant time operations for each character. The time complexity is O(n), and the space complexity is O(1), since the prefix_count dictionary only requires storage for 1024 entries, corresponding to all possible bit masks. The chosen strategy for solving this problem is the optimized approach using bit masking. This method is preferred because it reduces the time complexity from O(n)³ to O(n), making it highly efficient and suitable for large inputs. The space requirements are minimal as well, since the bit mask only requires storage for 1024 entries, which is constant space. Moreover, the use of bit masking provides an elegant and efficient way to track letter frequencies and determine wonderful substrings using a prefix-based approach. When comparing this to the brute force method, the brute force approach, while simple to implement, is computationally prohibitive for larger strings due to its cubic time complexity. Other prefix-based techniques, such as using arrays instead of bit masks, could be considered, but they lack the elegance and efficiency provided by the bit masking approach. By combining the power of bit masking and the prefix sum concept, this strategy strikes a balance between efficiency and clarity, making it the most suitable solution for the problem at hand. To solve the problem of counting wonderful substrings, we start by understanding what makes a substring wonderful. A substring is wonderful if at most one distinct character within it appears an odd number of times. The brute force approach begins with a straightforward intuition: generate all possible substrings of the given string word and check each one to see if it satisfies the wonderful condition. First, we extract all substrings by iterating through every possible starting index I and, for each I, iterating through every possible ending index j. This produces all substrings, such as a, and abc for a string abc. Next, we calculate the frequency of each character within a substring. Using a dictionary or an array of size 26, we traverse the substring and update the frequency count for each character. This prepares the data we need to evaluate the wonderful condition. Once we have the frequency counts for a substring, we check whether it meets the wonderful condition. To do this, we count how many characters in the substring have an odd frequency. If this count is 0 or 1, the substring is deemed wonderful. We then maintain a counter variable, wonderful_count, to track the total number of such substrings. For every substring that satisfies the condition, we increment this counter. Finally, after processing all substrings, we return the value of wonderful_count as the result. However, the brute force approach has significant inefficiencies. Generating all substrings requires two nested loops, resulting in an O(n)² time complexity. Additionally, counting character frequencies for each substring adds another O(n), leading to a total time complexity of O(n)³. Although this approach is conceptually simple, it is computationally expensive. To improve, we need to explore key insights around character frequencies and consider optimizations. A critical observation is that we don't need to track the exact frequencies of characters for each substring. Instead, we only care about whether the frequency of a character is odd or even its parity. This can be efficiently represented using a bit mask. A bit mask uses 26 bits, one for each lowercase English letter, where a bit is set to 1 if the corresponding character has an odd frequency, and 0 otherwise. Building on this concept, we can efficiently calculate results using a prefix XOR. By maintaining a running XOR of the bit mask for characters encountered so far, we can identify wonderful substrings. If two prefixes have the same XOR value, the substring between them is guaranteed to have even frequencies for all characters, making it wonderful. We can also handle cases where one character has an odd frequency by allowing one bit in the bit mask to differ. To implement this efficiently, we use a hash map to store the frequency of each prefix XOR value, enabling us to compute the result in linear time. The optimized approach begins by initializing a variable prefix _XOR to track the running XOR of the bit mask as we traverse the string. We also use a hash map, initialized with an entry for prefix _XOR equals 0 to handle cases where the prefix itself is wonderful. As we iterate through the string, we update prefix _XOR for the current character. This is done by flipping the bit corresponding to the character's position in the alphabet. Next, we add to the result the number of times this prefix _XOR value has already appeared in the hash map, as it indicates substrings where all character frequencies are even. To account for substrings with one odd frequency, we iterate through all 26 possible bits and check for XOR values where a single bit differs. For each match, we increment the result by the frequency stored in the hash map. Finally, we update the hash map with the current prefix _XOR value. This process ensures that all wonderful substrings are efficiently counted in O(n) time. When working with this algorithm, it's important to consider edge cases to ensure correctness. If the input string is empty, there are no substrings, so the result is 0. For a single character string, the result is 1, as any single character is inherently wonderful. For strings with all identical characters, every substring is wonderful since no character has an odd frequency. For mixed character strings, the algorithm correctly identifies and counts substrings based on the wonderful condition. The optimized approach is highly efficient, with a time complexity of O(n) due to the single traversal of the string and constant time operations on the hash map. The space complexity is O(1) for the bit mask and O(n) for the hash map, making it scalable even for large inputs. This combination of speed and efficiency makes the optimized solution well suited for solving the problem of counting wonderful substrings. The provided solution efficiently computes the number of wonderful substrings in the given string word. The key insight here is to use a bit mask to represent the frequencies of characters in the substring, where each bit corresponds to a character, A to J. A substring is wonderful if at most one character has an odd frequency, which can be checked by comparing bit masks. ###code explanation. 1. Initialization. Mask _count is a dictionary that keeps track of how many times each bit mask state has been encountered. It starts with 0, 1, because an empty substring is considered valid. Mask is initialized to 0, representing the bit mask for an empty substring. Wonderful _count is initialized to 0, it will store the total count of wonderful substrings. 2. Iterate through word. For each character in word, calculate its bit mask representation relative to the current state by flipping the corresponding bit. This is done using mask equals 1, ord, char, ord, a. 3. Count wonderful substrings. Add to wonderful _count the number of substrings ending at this position that share the same bit mask. These are substrings where all character frequencies are even. Check for substrings where exactly one bit is flipped, one character with an odd frequency. This is done by iterating through all 10 possible bits, representing A to J, and checking mask 1i. 4. Update mask _count. Increment the count of the current mask in mask _count. This ensures that future substrings can reference this state. 5. Return result. After processing all characters, wonderful _count contains the total number of wonderful substrings. ###efficiency. This algorithm is highly efficient with a time complexity of O(n), where n is the length of the input string. The key optimization comes from using bit masks and a hash table to track states, avoiding the need to explicitly generate and check all substrings. This makes it suitable for large input sizes. Here, we begin by importing the necessary libraries and defining the solution class, which contains the wonderful substrings method. This method takes a string word as input and calculates the total number of wonderful substrings. To accomplish this, we use a hash map called mask count to keep track of the frequency of each bit mask state. Initially, we store the mask 0 with a count of 1, representing the scenario where no characters have been processed yet. Next, we initialize two variables, mask, which tracks the current bitmask state of character frequencies, and wonderful count, which will store the total count of wonderful substrings. As we iterate over each character in the input string, we update the mask by flipping the bit corresponding to the current character. This is done using the XOR operator in combination with a bit shift based on the character's position in the alphabet. We then calculate the number of substrings ending at the current character that have the same bitmask state by looking up the mask in our hash map. To account for the condition where at most one character has an odd frequency, we iterate through all 10 possible bits, flipping each one individually, and add the corresponding counts from the hash map to wonderful count. Finally, we update the hash map to reflect the new count for the current mask state. The last step of the method is to return the wonderful count, which now contains the total number of wonderful substrings in the input string. This concise yet efficient approach leverages bit manipulation and a hash map to track the bitmask states, ensuring that we process the input string in linear time. By carefully managing the mask transitions and accounting for both exact matches and masks with 1-bit difference, we ensure that all valid substrings are counted accurately. This completes the implementation of the solution, providing both clarity and efficiency for solving the problem. To solve this problem, we start by initializing 3 key variables. First, we have mask_count, which is a dictionary tracking how often each bitmask has been seen. Initially, it contains just the base case where the mask is 0, encountered once. Next, we define mask, starting at 0 to represent no characters processed yet. Finally, we initialize wonderful_count to 0, which will store the total number of wonderful substrings we find. Now, let's process the first character, a. We update the mask by flipping the bit corresponding to a. This is done using the XOR operation, and the new mask becomes 1, represented in binary as 0000000001. Since this exact mask hasn't been seen before, adding it to wonderful_count doesn't change the count yet. However, we also check for masks where exactly 1 bit is flipped, as these represent potentially valid substrings. Flipping the bit back to 0 gives a mask of 0, which has been seen once in mask_count. This contributes 1 to wonderful_count, bringing the total to 1. Finally, we update mask_count to include the new mask of 1, which has now been seen once. The updated mask_count is 0, 1, 1, 1. Next, we process the second character, another a. Flipping the bit 4 out again toggles the mask back to 0, as flipping a bit twice returns it to its original state. This mask has been seen before, so we add the count for mask 0 from mask_count, which is 1, to wonderful_count. This brings the count up to 2. We then check for masks with 1 bit flipped. Flipping the bit 4 out again gives a mask of 1, which has been encountered once before. Adding this to wonderful_count increases the count by 1, making it 3. Finally, we update mask_count to reflect that mask 0 has now been seen twice. The updated mask_count is 0, 2, 1, 1. Moving on to the third character, b, we toggle the bit corresponding to b. This changes the mask to 2, represented in binary as 0000000010. Since this mask hasn't been encountered before, adding it to wonderful_count doesn't change the count. We then check masks with 1 bit flipped. Flipping the bit 4b gives a mask of 0, which has been seen twice in mask_count. This contributes 2 to wonderful_count, increasing it to 5. Flipping the bit 4a instead gives a mask of 3, which hasn't been seen yet, so it doesn't contribute to the count. Finally, we update mask_count to include the new mask of 2, which has now been seen once. The updated mask_count is 0, 2, 1, 1, 2, 1. The final output for the string ob is 5. Now let's examine another example, with the input string ab. As before, we begin by initializing mask_count with 0, 1, mask as 0, and wonderful_count as 0. We then process the first character, a. Flipping the bit 4 updates the mask to 1. This new mask hasn't been encountered before, so adding it to wonderful_count doesn't change the count. We then check for masks with one flipped bit. Flipping the bit 4 back to 0 gives a mask of 0, which has already been seen once in mask_count. This contributes 1 to wonderful_count, making it 1. We then update mask_count to include the new mask of 1, which has now been seen once. The updated mask_count is 0, 1, 1, 1. Next, we process the second character, another a. Flipping the bit 4 again toggles the mask back to 0. This mask has been encountered once before, so we add its count from mask_count, which is 1, to wonderful_count. This brings the count up to 2. Checking masks with one bit flipped, toggling the bit 4 gives a mask of 1, which has been seen once before. Adding this to wonderful_count increases the count by 1, making it 3. Finally, we update mask_count to reflect that mask 0 has now been seen twice. The updated mask_count is 0, 2, 1, 1. Next, we process the third character, b. Flipping the bit corresponding to b updates the mask to 2. This mask hasn't been encountered before, so adding it to wonderful_count doesn't change the count. Checking masks with one bit flipped, toggling the bit 4b back to 0 gives a mask of 0, which has been seen twice in mask_count. This contributes 2 to wonderful_count, bringing the total to 5. Toggling the bit 4 instead gives a mask of 3, which hasn't been seen yet, so it doesn't contribute to the count. We then update mask_count to include the new mask of 2, which has now been seen once. The updated mask_count is 0, 2, 1, 1, 2, 1. Finally, we process the fourth character, another b. Flipping the bit 4b again toggles the mask back to 0. This mask has been seen twice before, so we add its count from mask_count, which is 2, to wonderful_count. This brings the count to 7. Checking masks with one bit flipped, toggling the bit 4b gives a mask of 2, which has been seen once before. Adding this to wonderful_count increases the count by 1, making it 8. We then update mask_count to reflect that mask 0 has now been seen 3 times. The updated mask_count is 0, 3, 1, 1, 2, 1. The final output for the string ab is 8. To analyze the time complexity of our solution, let's focus on the operations performed within the loop that iterates over the string word. First, updating the mask using the XOR operation is an O1 operation since it involves a simple bitwise calculation. Next, when we count substrings with the same mask using mask_count.get, mask 0, this is an average O1 operation because dictionary lookups are highly efficient. We also have a loop that goes over 10 possible bits, from 0 to 9, to check for masks with at most one odd frequency. This inner loop performs a dictionary lookup for each bit, which again takes O1 time per check. Since this is done for a fixed 10 iterations, the total contribution is O10, which simplifies to O1. Finally, updating the mask count in the dictionary is another O1 operation. Since all these operations inside the loop are O1, and the loop itself runs n times, once for each character in word, the overall time complexity of the solution is O(n). Now, let's evaluate the space complexity. The largest contributor to space usage in this solution is the mask_count dictionary. Here, the mask is a 10-bit number because it represents the frequencies of up to 10 letters, from A to J. This means there are at most 2 to the power of 10, or 1024, unique masks that could be stored in the dictionary. Since this number doesn't depend on the size of the input string word, the space used by the dictionary is considered O1, or constant space. Additionally, we use a few auxiliary variables such as mask, wonderful_count, and the loop index I. These variables also require constant space. Therefore, the total space complexity of this solution remains O1, making it highly efficient in terms of memory usage. Let's compare this optimized approach with a brute force method. A naive solution would involve generating all possible substrings of word and checking each one to see if it's wonderful. Generating all substrings would take n squared time, as there are n squared substrings, and checking each one could take up to n time to count character frequencies. This results in an overall time complexity of n cubed for the brute force approach. In contrast, the optimized solution achieves n time by using bitwise masks to efficiently represent character frequencies and leveraging a dictionary to store intermediate states. This eliminates the need to explicitly generate substrings and avoids redundant checks. Furthermore, the time complexity remains n across best, average, and worst cases, as the algorithm processes each character and word exactly once, and the operations within the loop are independent of the input's content. The mathematical foundation of this optimization lies in using the 10-bit mask to track frequencies efficiently. By flipping bits and checking a constant number of possible masks, we avoid the combinatorial explosion of substrings while maintaining correctness. A common pitfall when working on this problem is failing to account for edge cases. For example, what happens if the input string is empty, has just one character, or consists entirely of the same character repeated? These scenarios can break algorithms that assume the input is always diverse or sufficiently long. Testing edge cases explicitly is crucial to ensure your solution is robust. Another mistake is relying on nested loops to generate all possible substrings. While this approach might seem straightforward, it results in a time complexity of n cubed, which becomes impractical for large inputs, especially when constraints reach 10,000 or more. Lastly, misunderstanding the wonderful condition can lead to errors. Some solutions incorrectly apply the condition to the entire string rather than to its substrings, which results in incomplete or incorrect answers. Defining the condition clearly and applying it correctly is key to solving this problem successfully. Another area where mistakes often occur is in the failure to utilize optimization techniques like the sliding window approach or hash-based methods. Instead of recomputing properties for every possible substring, which leads to significant redundancy, these techniques allow you to reuse prior computations for improved efficiency. Similarly, incorrect state representation is a frequent issue. For instance, using overly complex data structures like frequency arrays when a simpler approach, such as bitmasks, would suffice. Bitmasks are particularly effective here because they simplify the code, reduce memory usage, and make it easier to track the properties of substrings. Avoiding these pitfalls can make your solution both more efficient and easier to debug. When preparing for interviews, it's helpful to recognize common patterns in substring problems. Techniques like sliding windows or prefix sums are widely applicable and can significantly reduce time complexity, often bringing it down from n cubed to n or n squared. State compression is another powerful optimization. For example, you can represent the state of a substring, such as the frequency of characters or whether their counts are odd or even, using a bit mask. This not only reduces memory usage but also simplifies the process of checking conditions. However, it's important to consider trade-offs. While hash-based solutions, like using dictionaries or sets, are generally easier to implement, they can consume more memory. On the other hand, bitmasking is highly efficient but may be harder to debug. In interviews, it's critical to explain your thought process clearly, including why you've chosen one approach over another, especially when balancing time and space complexity. If you're looking for related problems that reinforce the concepts used here, several LeetCode challenges are worth exploring. For instance, Problem 3 focuses on finding the longest substring without repeating characters, while Problem 395 examines substrings where characters repeat at least k times. Problem 424 deals with replacing characters in a substring to maximize repetitions, and Problem 992 involves identifying subarrays with exactly k distinct integers. These problems share techniques like sliding windows and bitmasking, making them excellent practice. When considering alternative approaches, brute force is the simplest to implement but comes with an exponential time complexity of n cubed. While it may work for small inputs, it's not suitable for larger constraints. Each of these problems and methods builds on the same foundational ideas but applies them in slightly different ways, helping you deepen your understanding of substring manipulations. For a more efficient solution, sliding window combined with a hash map is a popular technique. It achieves a time complexity of n by dynamically adjusting the window and reusing computations. However, this approach can be memory intensive, especially when storing large amounts of intermediate data. Bit masking offers another optimization, representing the state of a substring compactly and minimizing memory usage. With a time complexity of O(n), it's highly efficient, but implementing and debugging bit masking can be more challenging. Finally, prefix sums provide another balanced approach, reducing complexity to O(n)² in its optimized form. While it requires additional space for prefix arrays, it balances simplicity and efficiency. Each of these methods has its trade-offs, so choosing the right one depends on the problem constraints and your comfort level with the techniques. Great job completing this problem walkthrough. We covered the brute force and optimized approaches, analyzed their performance, and extracted key learning points. Remember, practice and pattern recognition are essential to mastering these problems. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!